Okay, let us get started with a general form for wavelet recursion, and we will also see through the inverse transformation and recovery after you have done the forward wavelet decomposition. Okay. So, let us start. Let us recall the two formulae we used for wavelet recursions. So, the first one was phi of 2 power j times t is 1/2 of psi 2 power j minus 1 times t plus phi of 2 power j minus 1 times t. Okay, this is straightforward, and then we look at a translate of this 2 power j times t minus 1 equals 1/2 of phi of 2 power j minus 1 times t minus psi 2 power j minus 1 times t. Okay, let us designate this set of equations as B. I hope we have not used B before, so some letter B. Okay. Now, we will try to derive a general procedure for wavelet decomposition of a signal from an arbitrary scale j. Okay, we start with some arbitrary scale j, and we will derive a general procedure for the wavelet decomposition. Now, since the set of these boxcar signals in the scale j, they form an orthonormal basis, that is phi of 2 power j times t minus k belonging to set of integers form an orthonormal basis for scale j. Right, we can write some function f j of t as summation k belonging to the set of integers a k phi of 2 power j t minus k, that is we are expressing this as a linear combination using the basis for the scale j, right. This is straightforward. Let me call this equation as C. Now, replace t by t minus k times 2 power minus j minus 1 in equation B, right. What will happen? So, basically instead of phi of 2 power j t, I have phi of 2 power j times t minus 2 k equals 1/2 psi 2 power j minus 1 t minus k plus phi of 2 power j minus 1 t minus k. Just a change of the variable. Similarly, for the translate by one time step is 2 power j t minus 2k minus 1. This is 1/2 of phi 2 power j minus 1 times t minus k minus psi 2 power j minus 1 t minus k. Okay, let us call this, say, some equation 1. Now, using equation 1 in C, we have the following. First, let us split equation C into even and odd terms. And then apply equation 1. This is a normal divide and conquer approach which people adopt, and you might have seen this in many algorithms in computer science. This is no different. So, what happens is as follows. So, f j of t equals summation k belonging to the set of integers a suffix 2k times phi of 2 power j times t minus 2k plus summa k belonging to the set of integers a 2k plus 1 phi of 2 power j times t minus 2k minus 1. Okay, this is no big deal for us. So, straightforward algebra. Now, let me call this equation 2. So, we apply 1 in 2. So, what is 1? Just if you want to recall, 1 is this equation which connects the phi function at a scale j, time translated by 2k and 2k minus odd and even translates, linking with the scaling function and the wavelet in a lower scale j minus 1, right. So, that is what we do here. So, we plug in 1 in 2, right. So, applying 1 in 2, we have the following. So, the equation is quite lengthy, so I am just going to use a different page. So, f j of t is 1/2 summa k belonging to the set of integers a suffix 2k. So, you have to put the brace outside, phi of 2 power j minus 1 t minus k plus psi 2 power j minus 1 times t minus k plus 1/2 summation k belonging to a set of integers a to k plus 1 phi of 2 power j minus 1 times t minus k minus psi of 2 power j minus 1 t minus k. Okay. Now, we can simplify this as follows. This is basically summa k belonging to the set of integers. What I do is I group the terms. So, I have a 2k minus a 2k plus 1 by 2 times psi 2 power j minus 1 t minus k plus summa k belonging to set of integers a 2k plus a 2k plus 1 divided by 2 times phi of 2 power j minus 1 t minus k. Right, I call this as equation 3. It really is a long lengthy equation, but I think what is important is we have decomposed it carefully by grouping them into odd and even parts. But I think what you should pay attention is just not what this equation is, but observe this term carefully and observe both the terms in this summation carefully, and this psi we know it is a wavelet function, right, and look at the coefficient of this wavelet basis. It is basically doing some difference operation here, a2k minus a2k plus 1 by 2, right. It is basically taking some difference operation, and it is basically this is basically the scaling, I mean scaling by a coefficient, right. The coefficient itself is basically taking some difference of some set of coefficients from a different obtained from a different scale, right, and you can imagine this is like our detail, right. If you were to detect some sharp edge in your image, maybe you take the difference between the image at that point and at the previous point to the left or to the right, right. Only when you take the gradient you can see that change, right. So, this is like a sort of difference operation, sort of like a difference operation. We will be making it more explicitly clear how these are linked to the filters, etc. Right. For example, if you think about the high pass filter, right, if it 1 minus z power minus 1 is a high pass filter, 1 minus the unit delay is a high pass filter, and if you look at its equivalent, right, it is basically if you take xk and filter it through that, you get xk minus 1. It is basically a differentiator. A high pass filter is basically a differentiator, and why it is a differentiator? Because it basically looks at successive differences in some way, simplest high pass filter first order, and that is why you can observe some change in the signal. The same thing is what, so that kind of interpretation comes through when you look through this detail, and this is basically some sort of averaging happening over the scaling function. So, this is sort of a loose sketch of this, but we will make it very precise when we further get down and interpret the wavelet transformation into filter banks. Okay. Now, fj of t is basically wj minus 1 of t plus fj minus 1 of t, where wj minus 1 of t is the wj minus 1 component of fj of t, and is a linear span of psi of 2 power j minus 1 t minus k, k belonging to the set of integers. And you can also interpret f j minus 1 of t. This is basically the v j minus 1 component of f j of t in the linear span of phi of 2 power j minus 1 t minus k, k belonging to a set of integers. This linear span is important. Now, let us be slightly more precise. By introducing a superscript j on all of these AKs, right. So, we generally took a scale j, we decomposed it into two components, one in wj minus 1, the other in vj minus 1 space, right. But the AKs are connected, AKs are the coefficients for the decomposition and they are connected. Now, if you were to program this numerically, all right, you would have to have to make it in a way that you could compute, right. So, therefore, these AKs they need to have a superscript or a subscript indicating which scale they belong to in the process of decomposition. So, we will make it a little more precise by introducing this superscript j on these AKs and try to link all of them. Now, fj of t is some k belonging to the set of integers ak of j phi of 2 power j t minus k, and this belongs to the space Vj, right. What I did is I just put the the superscript j here just to make it a little more precise. And now fj, we know, just if you just recall, this is basically wj minus 1 of t and fj minus 1 of t, and wj minus 1 of t equals sum over k belonging to the set of integers sum bk of j minus 1 psi of 2 power j minus 1 t minus k, right. I am just trying to expand this because this is a signal which is belonging to the space wj, where bk of j minus 1 is a2k of j minus a 2k plus 1 of j upon 2, right. We saw in that equation a2k minus a2k plus 1 upon 2 of psi of 2 power j minus 1 t minus k, right. We did this in equation 3, right. I am just rewriting that a2k minus a2k plus 1 with the superscript j and linking it with the coefficient in scale j minus 1, because this belongs to this is j minus 1, right, j minus 1. Clear? Now what we will do is we will do this similarly. We can write f j minus 1 of t as summation k belonging to set of integers. So, I will just use this as a itself, some a k, but I will use j minus 1 here to be little more precise, of phi of 2 power j minus 1 t minus k, that is all shift orthonormal translates of the basis function. This belongs to the space Vj minus 1, where ak j minus 1 is a2k of j plus a2k plus 1 at scale j upon 2. Right. What I did was nothing except expressing equation 3 that I had earlier by making it a little more precise by bringing this superscript indicative of the scale, so that when you decompose, you know which scale that function resides in or the signal resides in, and appropriately you have the coefficients which are appropriate to that particular scale. Okay. So, now we have a procedure for decomposition. We can proceed computing the recursion, it is a recursions for j minus 1, j minus 2 dot until 0 to obtain fj of t equals f naught of t plus summa I equals 0 to j minus 1 wi of t, right, and this gives us the forward decomposition procedure. Okay. So, given any signal, you just start with an appropriate scale, and from there you start decomposing the signal, and you can you get to whatever level of detail that you want to. Okay. So, we will stop here and then we will begin with the reconstruction step following this.